start. So welcome everybody to the first Astromeeting seminar of this season. So the speaker is Emanuele Contini from the University of Seoul, and I leave the word to Rita, who will introduce the speaker.
Yes, thanks. And it's a pleasure for us to have Emanuele here. Emanuele is associate professor, and he mainly focused on the simulation about the formation of an intracluster light in particular. And so I will leave the floor to you, Emanuele.
Yeah, I can introduce myself. So, first of all, let me thank Enrica, Rossella, and Marilena for inviting me here. It's a pleasure. Napoli is an amazing city, really. I enjoyed a lot walking through the streets. And I guess it's true what people say in Italy that vedi Napoli e poi muri. So you've done everything. It's really amazing. And Pompeii as well. So I studied in Padova, both bachelor and master degree. After that, I decided to move to Trieste, another amazing city, for my PhD, and I was supervised by Gabriella De Lucia and Stefano Borgani. Then, during my PhD, my main work was developing numerical simulations, building virtual trees, which are the input for my seniority model. But in terms of science, my main topic, which is also today's topic, was the implementation of the intracluster light in the seniority model. Then I moved to China for my first postdoc, because I don't know why at the time in 2014 I had this idea that China was a great country where to live in, and I was surprised that it's not. So I did postdoc around 3 years, and then I moved to Seoul for my second postdoc. And South Korea is much better than China, I would say. And then I have the brilliant idea to go back to China in the university, to know the observatory like before. And this was in the beginning of 2019, February. And everything was okay for a few months after that. You all know what happened, and I was there in China. So for a few years I could live there, then my wife couldn't join me. I couldn't leave China unless I resigned. So I resigned and I left China, and I reached my wife in Seoul, and after a month I found my almost old position, and now I'm a professor. At the time I was a postdoc. So let's start. I will talk about the formation of the intracluster light and the main properties of the ICL, and I will divide the talk in two parts. The first part is basically what we need to know about the ICL and what we already know. So I will talk about both observational and numerical methods to isolate the ICL, the main channels of its formation, and of course the most important properties. And then what I really find very interesting is the link between the ICL, how to use the intracluster light to know a little bit more about dark matter. The second part is just a few results of my last two papers. One was accepted during the night, last night, and the other one I submitted it yesterday, but I will talk a little bit about these two papers. So the intracluster light. What do we mean by ICL? The intracluster light is a diffuse component in galaxy groups and clusters. It is made of stars that are not bound to any galaxy, including the central one. So are just stars that fill the potential well of the dark matter, and they float here around in the cluster. This is an image that Rika knows very well. Fornas cluster. You will see the yellow stuff there between galaxies. That's intracluster light. Real difficulty you know the definition, it's made of stars that are not bound to any galaxy, including the BCG. The definition itself is easy. Isolating the LCL is another matter. The first difficulty is to mask the contribution of all of the satellites. And the last difficulty is to separate it from the BCG, because there is no a clear limit. This is BCG, this is ICL, they are embedded. However, there are different methods to try to isolate the ICL. Observationally speaking, people usually use surface brightest cuts or profile fitting, try to isolate the ICL from the BCG. In simulation, we have dynamical information, kinematic information, so it's a little bit easier for us. If you use similarity models, it's even much easier because it goes by construction. Basically, a similarity model is a code that solves a lot of differential equations at the same time. So every single property of a galaxy is just an array with different properties, and the ICL, as well as all the other properties, once implemented, the code knows the right amount. I don't need to separate it for the BCG and the other galaxies. So if you look at groups and clusters in the present in the local universe, the ICL is actually very abundant. It's not a component. It's not a component that you can discard or pretend it doesn't exist. Here is a plot from Farnell 2021. The STL fraction as a function of velo mass. Here is, I guess, my model. And a bunch of observational data and also simulation. You will see there is no a clear dependence on the cluster, on the mass of the cluster. But the important thing is that, observationally speaking, the fractional ICL can range between 5 and even 50%. So it's really, really important. If you go to higher redshift, this is, for example, in beginning this year, there was a new paper, the Zhu and Ji probed the fraction of intracluster light in 10 clusters, groups and clusters at high redshift between 1.2 and 1.8, and they found that it's comparable with the typical fractions that you find at redshift 0. So, which means that the ICL is already abundant and important at high redshift. They use it against my model, but you will see later that also my model predicts more or less the same amount of ICL at high redshift. So observationally, you can use surface brightness cuts. The problem is that it's very sensitive to the cut that you choose. This is an example. ICL fraction as a function of the radius. If you use higher cuts, you are getting more ICL probably than expected. If you use a lower cut, the fraction of ICL drops, and so depends on. It's very objective. There is no clear cut that you can use. Different authors use different cuts. What I prefer a little bit more is the profile fitting, because you can choose 1, 2, 3 different components, usually celsius profile fitting, and you can separate as much as you can. You can separate the ICL from the BCG, and also what is called the transition region between the BCG and the ICL. This is just an example. Probably profile fitting is better than a simple cut. In numerical simulation, it's much easier because we have the dynamical information, so you can draw the velocity distribution of every single particle, and they obey two different Maxwellians, so you can isolate the ICL from the BCG. This is, of course, only possible with the simulation. So here is my model. I started in 2012 to implement the formation of the SEL in my model. And I started with two simple assumptions. The first one, I said, probably the SEL is forming through stellar stripping. So I had to put something that could describe the stellar stripping in the model, and also by mergers during the violent relaxation process happening during mergers. Some of the stars can go directly to the SEL component. So stellar stripping is very easy. The code derives a tidal radius. If the tidal radius is so small to go within the bulge of the sun, if it's larger, so that it ends up in the disk of the satellite, then only a part is stripped, and all the stars goes to the SEL component. Mergers, it's a simple but very simple recipe. During every single merger, major or minor, 80% of the mass of the satellite goes to the BCG, and 20% goes to the SEL component. The reason why 20%, because at that time we had control simulations, so we looked at every single merger and the distribution of the fraction that is lost during a merger peaked at 20%. So we used that percentage. There are, during the last 20 years, I guess, there have been a lot of processes involved to explain the formation of the intracluster line. Stripping of massive satellites, mergers, pre-processing. Pre-processing means that the SEL forms somewhere else, like in a group, and then during a merger between two halos, the group is accreted by the biggest halo. In that case, it carries also the SEL within it, and we call it pre-processing. There was also in situ star formation and disruption of dwarf galaxies. Now, in situ star formation has been ruled out because, observationally speaking, it accounts for no more than 1% of the SEL. Disruption of dwarf galaxies is important in terms of numbers of satellites that you can destroy, but not in terms of mass. So this channel doesn't contribute to the SEL in terms of mass, but it destroys a lot of dwarf galaxies. So basically, we end up with the three major channels: stripping of satellites, mergers, and pre-processing. The first two are direct way to form ICL, in the sense that you have a cluster, the ICL forms there. Pre-processing is ICL that is accreted later and anyway formed by the other two channels. So it's an indirect way to increase the fraction of ICL. But this channel is very important. If we plot the fraction of ICL accreted as a function of BCG mass, if you think the large BCG stay in large clusters, the fraction of ICL that comes from pre-processing can reach 40% in bigger clusters. So it is important. While mergers, they do not contribute too much, between 10 and 20% more or less. Most of the ICL, around 85% on average, comes from stripping of satellite galaxies. Which kind of satellites will we see in a while? The ICL, the fraction of ICL must depend somehow, because if you plot the fraction of ICL as a function of envelope mass, there is no dependence, but there is a huge scatter. At the time, I tried to understand what is giving the scatter in the relation, and the concentration seem to be a good property to explain the large scatter. Indeed, this is the fraction of ICL as a function of halo concentration. The concentration of the halo is the ratio between the virial radius and the scale radius while you assume an average wide profile. It means that the larger the concentration, the more relaxed or virialized the halo is. So, and the concentration can explain a huge part of the scale, considering the formation time of the halo, when the halo already assembled like 50% of its mass. These two properties are actually linked to each other. Also, if you have an older dark matter halo, probably it had more time to process ICL, so the fraction of intracluster light is higher in older objects. So what kind of galaxies contribute the most to the ICL? At that time, if you draw the contribution given by the mass of the satellite, focus on the blue one here, we see that around 70% of the ICL, the mass in the ICL, is coming from the stripping of intermediate massive galaxies. You can see it if you look at the metallicity of the ICL. Here they pick the typical metallicity of very massive, intermediate massive galaxies, which is in good agreement with the observation, not all of them, of course, but it's in a good agreement with many observers that say that most of the ICL is actually coming from intermediate and massive galaxies. And what kind of galaxies most to the ICL? I found in 2018 that if with morphology I use bulge to total ratio, so here you have disk galaxies and disky galaxies and ellipticals on the other side. Actually, our spirals are contributing the most to the formation of the ICL with stripping events that, let's say, just strip no more than 30% of the mass of the satellite at every single event. So the disruption of satellites, it's a very unlikely event. And the ICL forms pretty late. Here is the fraction of ICL at redshift 0 normalized, sorry, at different redshift normalized with the fraction at redshift 0. You can see here that we are more or less at redshift 1. Only 20% of the ICL was already formed, which means that if you take into account, consider all the history, the formation history and assembly history of a given cluster, its ICL will start to form after redshift 1, and then it proceeds pretty quickly. Here is my model. Here is Morant simulation of Morant et al. In 2007 that confirmed. Actually, I confirmed the simulation. If we move to the observational side, here is an example of free clusters, redshift between 0.3 and 0.4, 0.7, if I remember well. From Montes 3 in 2007, they wanted to show here is age and metallicity of BCG plus ICL as a function of the radial distance. They wanted basically to show that the ICL is younger and more metal poor than the BCG. They didn't separate the two components clearly. They just put a limit at 450 kiloparsec from the center, and they say here is BCG dominated and here is ICL dominated, and they show very clearly that the ICL is younger, yeah, and more metal poor than the BCG, which is in line with most of the models because the events that are more likely is just a simple tripping from the edge of the satellite, while the BCG is a little bit more metal rich. If you don't see any gradient here, it means that probably mergers are contributing the most to the ICL because they have the power to mix everything up. Having a gradient like this, it means that the stellar stripping probably is contributing the most. At least is the more plausible explanation for that. As I said in the beginning, one of the most difficult things is to separate the BCG from the ICL. Back 2 years ago, more or less, no, last year, I tried to do a simple exercise. I took the sample of from my numerical simulation, and I tried to plot the ICL from what the model tells me, and as a function of BCG plus ICL, I fit the relation, and then I try to compare the ICL true given by the model with that given by the fit in order to see whether there was like an empirical formula that observer can use to separate the BCG from the ICL, knowing the total mass, BCG plus ICL mass. It was a failure of success because if you go to, let's see here, the scatter, so how far the ICL that you recover from the formula is far from the real value. On group scales, here you can have an error that goes even more than 200%, but if you stay in clusters above in log 14.5, actually you can recover the right amount of ICL by 40% scat error, which is a good thing. This is valid only at redshift 1, but I already know that it's possible to extend at whatever redshift. So on cluster scale, it's possible to use this empirical formula to have just an idea of what the ICL would be given the total mass BCG plus intracluster light. Another way to separate the two components is by finding the typical radius of the transition between the two components. But again, there is no clear separation. Here the ICL starts. But there is a transition region where it's like a compromise between BCG and ICL. You try to lose as much as less as possible from the BCG and also ICL. Of course, whatever radius you take, you are gonna have more some BCG and you are losing some ICL. So here, many people try to do it, for Gonzalez and myself last year, and the typical transition radius of the transition, if you consider, for example, my model, if you consider the radius where the ICL starts to dominate by 90%, is around 60 kiloparsec from the center, but the scatter is huge, plus minus around 40, which means that you can go from 20 to 100 kiloparsec from the center, and the scatter is given by the fact that here I consider all the sample of values from group scale to cluster scale. Or the other way is by profile fitting, if you use at least 3 different components when you do the profile. You can decide, this is my transition radius. From here, I consider everything intracluster light to be intracluster light. In the last couple of years, 3-4 years, there have been people doing an interesting work, in my opinion, to try to use the ICL to study the dark matter. Montes Trujillo that try to link the distribution of the SEL with that of the dark matter. And also others try to do the same. Myself, last year, trying to find the typical radius of transition between the two components, and I linked it to the dark matter by it was an assumption. I said the SEL follows the dark matter distribution with a different concentration. It's more concentrated than the dark matter. Then I took the model, and I got the result that I showed you before. Just a few examples. For Montesquieu in 2019, they linked the distribution of the SEL with the dark matter with quantity that gives you an idea of how far are the distribution, the SEL distribution, or two distribution in general. And what they found in 6 different clusters, they found that on average the SEL is distant, like the distance between the two distributions, SEL and dark matter, is around 25 kiloparsec, much better than X-rays. So if in the past people were using X-rays, so you all know the problems with X-rays, the SEL is a better way to study dark matter, at least compared to X-rays. And the same exercise was repeated by using numerical simulation, which confirmed the results of Montesquieu. So it's possible to use intracluster light to study dark matter. So now let's move to the second part. Just a second. The SEL can tell us more information about the dynamical state of its host. For example, Rossella last year published an amazing paper that I liked a lot. She studied the fraction of SEL as a function of Elon mass for a bunch of groups, if I remember well. Fully groups. Yeah. A few clusters as well. And they found a very, very, very weak, can I say that? Weak correlation with Elon mass. But the interesting thing is that if you want to link the SEL with the dynamical state of the cluster U, and you need an observable to do that, one good candidate is the fraction of early type galaxies, in the sense that if early type galaxies are more abundant in an object, it means that probably that object is older than others. And they found a nice relation. So the fraction of ICL actually depends on the fraction of early type galaxies in cluster. And Rossella also used this argument to say that probably the ICL forms in groups, and it's later accreted in cluster on later stages, which is in the sense that pre-processed material is important. Yes, we already saw it contributes a lot, even 40% of cluster scale. My idea is that the formation of the intracluster light is actually linked to the concentration of the halo. So if the concentration of the halo is the ratio between the virial radius and the scale radius, it gives you an idea of how relaxed is is a cluster. So if the concentration is high, it means that the cluster is more relaxed in the final stage. Okay, so I use this argument to prove that the concentration is driving the formation of the intracluster light. And here we go. This is a simple distribution. I had last year I developed a set of cosmological simulations with different boxes. The biggest one is 200 each 200 megaparsec each side, and I ended up with a sample of halos more than 2,500 halos with mass above in log 13. This is a distribution, and I use it to prove that the concentration is driving the formation of the ICL. This is the simple distribution of the fraction of intracluster light at redshift 0. I ended up with an average of 35% plus minus 12%. The interesting thing here, and nobody showed before, is that this is a Gaussian, which means that all the processes that are responsible for the ICL, for the formation of intracluster light, are stochastic. And indeed, they are, because mergers and stellar stripping are the candidates. When I plot the fraction of ICL as a function of halo mass, and I divide the sample of halos in different ranges of concentration, from blue to red, the concentration is increasing. You can see that, first of all, there is not a clear relation with halo mass. It increases a little bit up to group scales in log 14, and then on a constant value of around 40%. But the interesting thing here is that there is a trend with concentration, in the sense that have an higher fraction of intracluster light, which is a little bit more clear. Here, the fraction of ICL as a function of halo concentration, and this is the relation. It's plausible because if stellar stripping, like I'm gonna show in a while, is the channel responsible the most for the formation of the ICL, the concentration when satellite galaxies reach the innermost region of the cluster, their tidal forces, if you have more concentrated halo, tidal forces are stronger. And so the probability to strip a satellite galaxies gets higher. And that's why more concentrated halos have a higher fraction of ICL. This is another way to see it. From this, I divided my sample of halos in 5 different bins, and I said, okay, in each bin, let's see how many, the fraction of halos that have fraction of ICL and concentration above the average at the same time, and below the averages at the same time, is the blue one. So basically, it's a way to look at the efficiency of the concentration in explaining why, in explaining whether or not it's driving the formation of the ICL. And you can see that on average, 70% of the clusters, the objects in general, in my sample, have fraction of ICL, a concentration that goes in the right direction, in the sense that the fraction of ICL and concentration are both higher than the average or below, or lower than the average. And then I moved to prove that my model actually can explain the fractions of ICL that we observe at higher redshift, even a redshift almost 2. These are a bunch of observed data from redshift 0 to higher redshift. You can see here that my model, the black line with the standard, predicts that the fraction of ICL is already important at higher redshift, and it's almost stable. You don't see a real trend with the For what concerns the channels for the formation of the ICL, there are 3 different channels: stripping, mergers, and pre-processing. Here is the power of stripping, which means the fraction of ICL that comes from stripping, comes from mergers. The sum of these two is 100%. So stripping is way more important than mergers at any redshift, while pre-processing, so form somewhere and then later treated, is stable with a redshift on around 20%. So the most important channel is definitely stellar stripping, and that's why the concentration is driving the formation of the ICL, because stripping is very sensitive to the concentration. If we look at the formation time of the ICL, here is defined as the time that the ICL was, I don't remember, 50%. At the time that the ICL was 50% of the final intracluster light at redshift 0. You can see there is no dependency with the mass. But the interesting thing is that, again, like with the concentration, there is the trend that with the formation of the halo. So halo that forms late, its ICL starts to form late. If they form very early, also the ICL forms pretty early. So they basically go in parallel. And here, I guess it's my last slide, is the efficiency in forming ICL. There is, as a function of halo mass, this is the ratio between the ICL and the halo, the mass of the halo, not the typical fraction ICL mass divided by the total stellar mass. This is just the mass of the halo. Basically, is the fraction is the trend is flattened, so there is no trend here, which means that halos are equally efficient in forming ICL. But if we study the same thing as a function of the redshift, you see that there is an increase of efficiency in forming ICL that goes accelerate after redshift 0.5. It's a little bit almost stable at higher redshift, so the ICL is starting forming a little bit piece by piece, and then after redshift around of the ICL. So here is my take-home messages. Just 1 minute for a summary of the most important things. The ICL forms very late after redshift 1. Through mainly stellar stripping of satellite galaxies, just a little bit of contribution from mergers. And the ICL that a halo or cluster can get from outside, which means during the assembly history of the halo, can be as important as 40% in big clusters. But the most important thing is that the ICL forms through stripping of intermediate massive galaxies. So I stop here and I take questions.